Good day, everyone. Welcome to the 5th International Symposium on Intelligent Manufacturing and Mechatronics presentation on oil palm fresh fruit branch ripeness detection using the YOLOV6 algorithm. Prepared by me, myself, Alfi Khan Chaudhary, supervised by Ms. Wanzaila Binti Wansayed and TS Dr. Sara Atifa Saruchi. Alright, so the table of contents for today are: firstly, the introduction of our topic, then the problem statement, objectives, followed by the literature review, methodology, results and discussion, and lastly, the conclusion, future works, and references. Alright, moving on. Firstly, the introduction. What is oil palm fresh fruit branch ripeness? Oil palm fresh fruit branch ripeness refers to the stage of ripeness of the fresh fruit branches, FFBs in short, of oil palm trees. The capacity of oil palm production is directly affected by the ripeness of FFBs upon harvesting. Conventional harvesting standards rely on rigid harvesting scheduling as well as the number of fruitlets that have loosened from the branch. Harvesting is usually done every 10 to 14 days, and an FFB is deemed ready to be harvested when at least 50% of its fruitlets have loosened from the branch. Alright, moving on. So, here we can see 4 stages of oil palm ripeness. Alright, so first we got the unripe, then we got the underripe, then we got the ripe, and then we got the overripe. So the unripe is the one which has no oil content according to research papers and other researches. Alright, the underripe one has minimum oil content, which is not the best probable one to choose for harvesting, which is this is not the best one to choose for harvesting. Next we have the ripe one. So ripe one is the best probable one for harvesting as it has the most oil content. Lastly, we have the overripe one after the ripe stage where the oil content deteriorates, so this is also not suitable for harvesting, the overripe one. Alright, moving on. So the problem statement. Nowadays, oil palm fresh fruit branches are harvested by human graders as part the fruit surface color and the number of loose fruits on the ground as a measure of the ripeness level. However, relying heavily on human graders would result in misclassified branches due to factors such as the position of the FFBs on the trees. Let's say some of the FFBs might be hidden behind the branches of the trees, the height of the trees. For example, on taller trees, the FFBs might not be clearly visible to the human graders, unclear vision because of the surrounding weather, lighting conditions, incorrect count of the number of loose fruits on the ground, and so on. These misclassifications might result in the harvesting of unripe FFBs, which as a result would reduce the profits of the oil palm plantation companies due to the production of low quality oil palm. Alright, next we have the objectives. So firstly, our aim was to collect oil palm fresh fruit branches image dataset from a real oil palm plantation site and then process the image dataset. Then our goal was to develop deep learning models in order to detect the ripeness of the oil palm fresh fruit branches using two YOLOV6 algorithm models, namely YOLOV6S small and YOLOV6M medium. We will explain more on these two models later in our methodology section. Alright, and our last objective was to validate the oil palm ripeness detection performance of the two proposed YOLOV6 models using an unseen image dataset. Alright, moving on. So the literature review. So as you can see, in the last decade, starting from 2011 to 2020, a lot of research papers on oil palm fruits using deep learning had been published by researchers worldwide. Major deep learning algorithms applied in the oil palm industry include algorithms like the support vector machine, SVM, artificial neural network, ANN, random forest, RF, convolutional neural networks, regression, and classification and regression tree card in short. Alright, with many key performance indicators were utilized in order to achieve various objectives for oil palm plantation and processing. With the introduction of You Only Look Once YOLO, the goal was to improve on real-time object detection. YOLO computes several bounding boxes and predicts class probabilities for those boxes using a single neural network for each box. While training on entire images, YOLO directly enhances detection performance when compared to traditional object identification approaches. The unified framework has various advantages. Alright, moving on. Then we have the methodology. So, first, our, our task was to dataset collection and to label the dataset. That's it. So, first, we collected the dataset from plantation within the Selangor region of Malaysia. We divided the dataset into four classes, namely unripe, underripe, ripe, and overripe. Lastly, we labeled all the dataset images using the misclassified annotation toolbox. So as we can see in the image here, this is the um, GUI or graphical user interface of the MakeSense.ai toolbox. So here, first we uploaded the images, all the images, then we used a box to select the um, FFB, and then we selected the class of it. So we got four classes: unripe, overripe, underripe, and ripe. We selected the ripe one as this is the ripe one. Then we downloaded all the labels and used them for training purpose. Alright, moving on. Next we have the proposed YOLOV6 algorithm models. As we know from before, it's YOLOV6s and YOLOV6M. Alright, now the YOLOV6 architecture. Alright, the YOLOV6 architecture employs plenty of new approaches to achieve state-of-the-art results. This can be summarized into 4 points: anchor free, hence provides better generalizability and costs less time in post-processing. The model architecture YOLOv6 comes with a revised, reparameterized backbone and neck with decoupled head for efficiency, and lastly ensemble learning for better performance. And the architecture of the YOLOv6 algorithm can be seen here in the image. Alright, next up we have the difference between the proposed YOLOv6 algorithm models. Alright, firstly, the YOLOv6 algorithm family has a list of models, namely the YOLOv6n, nano model, YOLOv6s, small model, YOLOv6m, medium model, and lastly YOLOv6l, large model. This study utilized the YOLOv6s and YOLOv6m models. The single path structure works better for the YOLOv6s model than the multi-branch structure in terms of accuracy and speed. As a result, a CSP stack rep block with a channel coefficient of 1/2 serves as the building block for the YOLOv6s model. Despite having more flops and parameters than the multi-branch structure, the single path structure might be faster to operate because of its higher level of parallelism and relatively smaller memory footprint. Multi-branch structures outperform single path structures for the YOLOv6m model in terms of accuracy and speed. As a result, a CSP stack rep block with a channel coefficient of 2/3 serves as the building block for the YOLOV6M model. Alright, so this is the difference between two models that we have used. Next up, we have the training and evaluation parameters. So training parameters are, firstly we use 100 epochs for training. Our batch size was 16. Our image size was 416, and we use pre-trained YOLOV6 weights for both of the models. Then for evaluation parameters, our main evaluation parameters were precision of the detection, F1 score of the detected object, frames per second or FPS in short, and lastly unseen image dataset detection accuracies. Alright, moving on. Results and discussion. So as we can see here, the precision of the YOLOV6S and YOLOV6M models, F1 score, frames per second. Then we have the unseen overripe image dataset accuracy, unseen ripe image dataset accuracy, and so on. Alright. As we can see that the precision of the YOLOV6M model is better than the YOLOV6S model. So as an explanation of this, what I would say that the YOLOV6M model is determined as the best performing model for detecting oil palm fresh fruit branches due to its highest detection accuracy in detecting 3 of the 4 oil palm fresh fruit branches classes successfully. The trained YOLOV6M model has a precision of 36.9%, F1 score of 33.1%, and lastly a frames per second of 54 FPS. So since the accuracies for the YOLOV6M model are better than that of the YOLOV6S model, we have chosen the YOLOV6M model as our best probable model for our cause. Alright, moving on. Lastly, the conclusion. So in this research paper, two YOLOV6 models, namely YOLOV6S and YOLOV6M models, were utilized and compared in order to find the best suitable YOLOV6 model for real-time oil palm fresh fruit branch ripeness detection. The dataset for the training purpose was collected from plantations within the Selangor region of Malaysia. After training both the models for 100 epochs using Tesla K80 GPU inside the Google Collaboratory, the models were compared in terms of the precision of the models, recall, F1 score, mean average precision, training time, inference speed time, frames per second, and non-maximum suppression time. And lastly, the detection accuracy was also analyzed using the unseen images dataset. Based on the comparison results, the YOLOV6M model outperformed the YOLOV6S performance in classifying the oil palm fresh fruit branch ripeness stages. Even though we mentioned about all these parameters in the conclusion, the major parameters that were utilized to detect the compare the two models were the precision, F1 score, um, frames per second, and lastly the de detection accuracy using unseen images dataset. Alright, moving on, future works. Alright, so in case of future works, we would like to include training the YOLOV6M model with more than 500 epochs using better GPUs like the Tesla T4 GPU of Google Collaboratory in order to achieve accuracy above 90%, as higher accuracy is key to object detections in real-time situations. Moreover, the dataset shall also be improvised with more images like images of oil palm FFBs high up on the tall oil palm trees. The improvisation of the dataset shall also increase the accuracy of the YOLOV6M model significantly. Lastly, the trained YOLOV6M model shall be integrated into our mobile phone application in order to implement the oil palm FFB ripeness detection in real time directly inside the oil palm plantation sites. That's all from my side. And as you can see the reference at the end. So that's it from my side. That's all. Thank you so much. Thank you. Thank you.